Good morning, dear students. Today we shall discuss about an important concept in mechanics, that is relative velocity. What is meant by this relative velocity? We all know what is meant by velocity. It is the rate of change in the position. When a body is moving, when its position is changing, then with respect to time, we account for what is known as the velocity there. See, the change in position itself is a relative term here. Change in position with respect to whom is the question. The one who is observing, the observer, becomes important. Whether the body is changing its position really or not, it all depends upon how the observer is making the observation. With respect to him, it appears to be changing, then he says, yes, it is moving. With respect to him, it is not changing its position, he will say it is not moving. I give an example. We are there on the in a compartment, suppose we are there. In the compartment, when you are traveling, two passengers which are there, one beside the other, we find each of us are at the same position with respect to each other. If you say whether where he is, he says he is besides me. Always the distance between you being the same. Your separation is not there between you and the other passenger with respect to time. With the time, the separation remains constant. Then we find both are not in motion, they say. For example, I show it in the same thing in the figure here. Suppose there is a man here, there is a man here, and this compartment is there. Whether this compartment is moving or at rest, whatever the case may be with respect to the surroundings outside, if this A and B are in these positions, and with respect to each other they are at the same position always, then A says B is not moving, B says A is not moving. Suppose it is a compartment which is moving on the rails in a direction like this. Even then they will say the same thing. Both of them say that we are with respect to each other at rest. We are not moving. What is happening actually? The observation is with reference to the observer here. As the observer observes, as he sees, from his standpoint, we find the velocity there. So that such a velocity is called relative velocity. So though the body is moving on the road there like this, the velocity of A with respect to B, velocity of B with respect to A is zero. That means they are not moving with respect to each other. The observer is important therefore. Velocity of B as observed by A, velocity of A as observed by B. The observer becomes very important. You know, whenever you want to measure the velocity of any body, naturally the observer must be there. Without observer, what will you measure? The observer has to measure the velocity with his own eyes, with his own mechanism what he has, with the instruments what he has. So the observer always fixes himself in a position. With respect to his position, he will try to check other things around him, how they are, whether they are changing their positions or not. If they are changing their positions, he will say yes, they are moving. Take for example another case. We are in a compartment here, the same way, and the observer is here, A, in compartment, and there is a tree outside here. The compartment is moving forward, the tree is behind that. You will see the tree is actually at rest, it is not moving, it is at rest. You know, it cannot move by itself. But the vehicle is also at rest, then only he will see the tree as at rest there. Suppose he is moving forward, he will see as if the tree is moving backwards. Actually he is moving forward. He will see the tree as if it is moving backward. Actually, you can really see this. When you are there in the compartment, when you see the platform outside, when the compartment is moving, you can see as if the passengers on the compartment, on the platform there, are moving backward. Actually, they are not moving backward, you are only moving forward. So this sort of a feeling, what you are getting as the velocity of the tree or the velocity of the passengers on the platform, is the velocity as measured by you, and that is what is called as relative velocity of those people, of those objects with respect to you. So relative velocity is therefore is the only thing that is there actually. There is nothing like actual velocity anywhere. We all try to find actual velocity and say the car is moving on the road with a velocity, means you consider yourself on the road and you don't move and the road is not moving, then the car is moving, we say. So velocity measured by you on a stationary road like that, when you are also still, that is what we call as the velocity of the vehicle there. So therefore the question is, the measurement of the velocity and the value of the velocity, its direction, everything depends upon how the observer is, where from the observer is making the measurement. Where is he fixing himself? Whether he is fixing himself on a stationary platform with respect to surroundings, or when he is also moving there. This difference comes into picture. Every day morning, it is a common sense that we have. When we get up early in the morning, we will see the sun at the east. And we see the sun going around the earth like that. By the time it comes to this evening, we see the sun at the west. It appears as if sun has moved from here to there. Actually, sun has not moved. The earth is moving. The earth is moving around, such that we are able to see the movement like that. Actually, earth is moving the other way around. Earth is moving from west to east like this, making a rotation like that. And therefore, the sun is appearing as if he is going from here to there. In the opposite direction it appears to us. This is what we are observing. Actually, this is not, we say sun rises in the east, we say it sets in the west, we say sun moves from here to here. All the sentences what you speak appear to be meaningful only when you consider yourself on the earth, if the earth is not moving. But the very illusion is because of the movement of the earth. So the observer's standpoint and the frame in which the observer is there, that decides whether the actual velocity with which he is observing them. That velocity is what is called as the relative velocity of the scene, of the observed, because of the observer, we will say, relative to the observer, with respect to the observer, we say like that. That is what is meant by relative velocity. Let us see how to exactly put into equations in our concept here. So what is required is, whenever there is an observer who wants to read the velocity will therefore becomes the velocity with respect to the observer. So observer must be in a particular frame. A frame means we think of a coordinate system. Say his observer is at this point O. With respect to him, this is the x-axis, this is the y-axis. Say. Suppose the observer A is here. We call him A, observer A. So this is the x-axis with respect to A. He is an observer. Then there is a particle, suppose there is a point here, P, which is moving like that with the velocity. It is moving like that, suppose there is a velocity for that. How do you know the velocity is there? Well, it is to be observed by the observer again, as I told you. Let us start that there is an object here at P. Observer from here is observing it. So, to make it much simpler rather, in one dimension, to understand this easier, let us say the observer is at the origin and the point is here, say, on the axis itself. It is moving along the x-axis, suppose. If the origin is not moving, that means if this coordinate frame is fixed, it is not having any velocity, it is still, then you will see the movement of the particle P. So let us say, therefore, this is the position of the particle P with respect to A. So it is with respect to the A. A measures the position from here to there along the x-axis like that. Suppose there is another coordinate system here. together with this one, where the x axis of this another observer having origin at O dash, here we call it as OB. He is having another x axis here, along with it y axis is here for him. This is the coordinate system. It is very much the same as that, only thing is the y axis is not the same in both cases, because we are trying to consider the movement along one dimension only here. So in this case, the observer here finds the position of the particle P as here. We call it as position of P as observed from B, the observer B. So the position is here like this as observed by A, as observed by B it is like this. They are not same. What is the difference? This is the difference. What is the difference? That the position of the observer B with respect to A. The observer is at this point now. His position with respect to this is that. He will not be able to see that. He will see from here, his point of view only, he will see the position of the particle P. So, position of P as observed by B is this one. Position of P as observed by A is this one. Position of B as observed by A is from here. These are 3 points which come up into the picture once you have two different observers. Now let us see about the movement, velocity. So at t is equal to 0 it is here, or some t it comes here. That means from here to here there is a displacement. Suppose this takes place in a time. So therefore we can differentiate the position as rate of variation of this position to get velocity. From the figure here itself you can see very clearly xpa is equal to xpb plus xba. What is meant by this? Position of A with respect to position of P with respect to A is equal to position of P with respect to B plus position of X with position of B with respect to A. That's what I wrote here in the figure. I wrote in the equation here. This can be given by a displacement. Position changes like this. Suppose initially all are at 0, say, or sometimes they are like this. Suppose that means this can be used as a displacement equation now. Position displacement equation. The position is along x-axis, it's changing along x-axis. You can see that. If you differentiate this now, you will get the velocity. So this is one velocity with time. This is another velocity with time. If you differentiate here, you can similarly differentiate this also like this. What you are getting now is velocity equation. This happens to be the velocity of P, that is this particle, with reference to A, as observed by A, as measured by A. Similarly, this becomes the velocity of the same particle P as measured by the observer B in the other frame, plus this is the velocity of the observer itself, who is B here, observer B here. That is what it is. Velocity of B with respect to A. So that is what the equations tell us. So this is what is meant by the relative velocity equation. Every velocity is only relative here, remember. There is nothing like absolute velocity there. Every velocity is with respect to one observer. And that observer, whether it is rest or not, that's the matter, ultimately that matters there. We come to it a bit later. Now see, this is velocity because of two observers we have here. One is at A, one is at B. This is velocity of P we are seeing now, observed by two of them. So this becomes the equation for relative velocity of P with respect to A. We call this as relative velocity of P with respect to A, we call like that. Similarly, this will be relative velocity of P with respect to B, and this is relative velocity of B with respect to A, or like that. So all the relative velocities only here. So that is what is the way we try to understand this. Suppose now A is not moving, A is at rest. That means this velocity, this fellow is not moving at all. Then this VB with respect to A becomes actual velocity of B. It becomes velocity of B only. Because A is at rest, his velocity is 0. That means when he is at rest only, he can see the actual velocity of the other one. Suppose he is standing on a platform, on a frame which is not all at rest. We don't even consider the movement of the earth there. Suppose. Then A is at rest. When he is at rest, what happens? The equation tells about the velocity of P actually. Because A is at rest, it becomes actual velocity there. If A is at rest, suppose, then this becomes actual velocity of P. That is equal to velocity of P with respect to B. This is again relative velocity with respect to B. Plus velocity of B there. Because there also A is not moving. Now you want to, there is only one thing that is moving here. That is, only one observer is moving, other observer is not moving here. So if you take this equation, velocity of P with respect to B, suppose you say, then what is it? It is equal to velocity of P with respect to actual velocity of P here, plus this comes the other side, becomes minus VB. So this becomes the reverse velocity of B. Actual velocity of P plus the reverse velocity of the observer. So now this is the relative velocity of anything. Suppose you observe anything. It is not because it is having that velocity. You will see your reverse velocity also in that. Its velocity and your reverse velocity in that. This is the condition what you have to understand along a direction. Suppose you are moving in a car. An example we take. You are moving in a car in the forward direction. There is another car also coming besides you in the same there. Both are with respect to the earth. Earth is not moving, suppose. Then what happens? What is the relative velocity between each of you? You are also moving, there is also moving. Suppose you are moving with different velocities. It is like this. There is a car moving, there is another car moving. This is moving with the velocity A, I call it as P, this is one part. This is another velocity, your observer is there, say it's like that. There are two things which are moving. These velocities are not same, they are different. But they are moving along the same direction, values are different. So what will be the observed velocity of this body as observed by B? He is observed here. So relative velocity of P with respect to B is equal to, this is the equation. Actual velocity of P that will be there, he will see his velocity also reversed in that. You have to find this equation vectorially by using the triangle law subtraction of vectors. So like this, the actual velocity minus the relative velocity of the observer, that means reverse velocity of the observer there. That's what's happening in the example I just now gave you. When the earth is moving in one direction, we will see as if the sun is moving in the opposite direction to us. Actually sun is not moving, only earth is moving there. You take the example of the cars only again. Suppose there are two cars now moving, one with a velocity v1 in this direction, another with another velocity v2 in the opposite direction. Then what will they observe? There is observer here, there is a driver here, there is a driver here also. What will the observation of the driver 1? He will find the velocity of this body as observed by him only. So we will get velocity of the second body with respect to the driver 1. That's what he will see. What will be that? Actual velocity of that with respect to the earth, on a stationary earth that is coming. So this body is coming on that, this car is coming on that. Plus the reverse velocity of this fellow also you will see there. The reverse of this also you will see here. That means actually it is in the opposite direction. So if you take this as V2, if you can refer to this direction is minus, this direction is plus. So actual velocity means here, this is minus V2. So you will find this as minus of V2 plus V1 if I put in the vector notation like that. That means he will see both velocities. The body is coming to him faster then what actually it is moving towards him? He is moving with some velocity, and he is moving, approaching in the opposite direction here. He is also approaching it in the opposite direction. So he will see his velocity also in that, as if it is coming in the opposite direction, because of this relative velocity concept. So he will see relative velocity like that. Similarly, suppose you take the velocity as measured by the driver 2. He sees this body moving. How will he see that body moving? Actual velocity of that plus v1 plus reverse velocity of this. Reverse of that means minus of minus v2. It's already minus v2, reverse of further that. That means reverse means in the positive direction now. So what he will get now here? v1 plus v2. This also v1 plus v2, this also v1 plus v2, but this is minus, this is plus. So this is minus v1 plus v2, this is plus v1 plus v2. So this he will observe as if it is approaching him with some of the two velocities, whereas the other one also will see the same way, but he is as if the other fellow is approaching him. This approach and that approach are in opposite directions. That's why plus and minus come there. So this is the concept of relative velocity. In one dimension it is very easy to understand like this. Suppose they are moving in the same direction, I told you the difference will be seen there. Suppose they are moving in two-dimensional plane now. I have told the movement in the one direction, along x-axis only we are given. Observer is moving along the x-axis, the body also is moving along the x-axis, both observers are in the same direction or opposite direction but along the same line. Now suppose another case. In two dimensions it comes. Observer 1 is here, observer 2 here. I may call it as A, I may call this B, say, observer B. This is the x-axis for B, this is axis for A, y-axis for B, y-axis for A. Now there is a particle here. This particle is moving. The position of this particle P is on the same lines what we said now. With respect to this observer is this. This observer sees as if the particle is here. That means he will see with the position vector r here, r of P with respect to A. The position of this particle is seen by B as if it is here. This is the position vector of the particle P as measured by B, as found by B. This is the position vector of the particle P with respect to B. Then what is this OA, OB here you can see? That tells you about the position of this second observer with respect to the first observer. That is position vector of B with respect to A. When there are two dimensions like that, in a plane like that, so by going by single coordinate, you have to go by two coordinates. That means you must think of a vector, direction also must be involved there. So you must write like that. The position must be given in two dimensions, like x direction, y direction also. This will find as if it is in this point here, this observer is here with respect to A. Now you can see in the picture now, RPA, that vector is equal to sum of these two vectors. Just like what you have seen in the case of one-dimensional position there. One dimension is along the x-axis. Now it is the vector notation along the position vectors now. So now you see here. Now you want to find out the velocity, relative velocity. Velocity of P with respect to A. Differentiate this one. That gives you the velocity of P with respect to A. and that differentiate RPB with respect to time, that gives you the velocity of P with respect to B, and differentiate RB with respect to A, the time, it gives you the velocity of B with respect to A. So the equations tell us, if you take d by dt of RPA is equal to d by dt of RPB plus RBA. There is nothing but the velocities now. That means velocity of P with respect to A is equal to velocity of P with respect to B plus the velocity of B with respect to A. Once again the same equation comes. So the concept is the same. Only thing is how to go about for the calculations depends upon the directions also involved there. So you must go through vector dimensions there. If it is only one direction, it is a simple addition or subtraction comes like that. If it is in a plane like this, you must take the help of the triangle law for the addition and subtraction here. So that is what is meant by it. A simple case is that so whenever the two observers are there, this you must remember. Suppose observer A, observer B, and he is there, only one fellow is moving, suppose he is moving there with the velocity B. He is not moving, actually velocity is 0, suppose. But this fellow sees as if this fellow is going back, like the example I told you. So velocity of A with respect to B is that. With this minus, VB will be there. He is moving forward as if he sees as if there is moving backward. Velocity similarly B with respect to A. This is the actual velocity of B here. That means B as observed by A is not moving, so he will see as if he is moving forward. So these equations are also in coordination with what I said now. Here only one body is moving. In this case we are taking both bodies moving there, both observers moving there. Here only one observer is moving here. So that is the case if you see. Take the motion in an example further. We take an example and see. In 2 dimensions we will see. Suppose there is a car moving here, car 1 here, car 2 here is moving. They are moving at right angles to each other. One is going towards east, say, and another is going towards north, say, like that, with some velocity, say. Say it is moving with velocity 3 meters per second. This is moving with velocity 4 meters per second in that direction. This velocity is with respect to the earth. So we call this as velocity C2 with respect to the earth, I call it. Actual velocity we call it, we simply put V2. This is actual velocity we call it, say. This is velocity C1. That means with respect to the stationary earth there. Now suppose this observer is seeing there. The driver of this car is seeing there how it is moving according to him. And that observer, the driver sees this car, how will he see? Same principle to be applied now. So velocity, now observer is, suppose observer is 1. We take observer 1. Velocity of C2 with respect to observer 1 we want now. Second car with respect to observer 1 we want, suppose. This is according to our notation what we said. Actual velocity of the car, that is Vc2 plus the reverse velocity of the observer minus Vc1. Now see in the picture how we will have it. Actual velocity of this is this, and the reverse velocity of this is in this direction like that. This is 4, this is 3. We have to find the sum of these two things vectorially. To get the triangle, you must show this parallel on this side here. Instead of showing here, we have to show that there. Because you have to account for the triangle law in order. So this plus that. That gives you this vector. This is velocity of C with respect to observer 1. See now. So what you will see, that means this fellow will see as if it is moving like this. Understand? So this will be the angle at which he is seeing it. Alpha I call it. What will be the velocity value you will get here? You must get a triangle here. There are right angles, therefore we can say velocity of C2 with respect to 1 is equal to, magnitude is equal to square root of 3 square plus 4 square. That is 5. So he sees as if it is moving with 5 meters per second at an angle alpha. What is the angle alpha here? Alpha is given by tan inverse 3 by 4. Some angle here. That angle is tan inverse 3 by 4. So it seems he is going like this, whereas the fellow is at right angle is going there. If he looks at him, it appears as if he is going like that in the diagonal direction there. So that is what this will tell you. Now let us find out what is the velocity of the observer as measured by the observer 2. What will be the velocity of the first body? That is this car. This is what we want to find out now. What will be that again? Same rule. Velocity of the observer, velocity of the first car with reference to the second observer is equal to actual velocity of the first car equal to actual velocity of the first car plus the reverse velocity of the observer. This is what the equation is. So now how to put it on the figure here? This is velocity, actual velocity, then reverse velocity. This is going up like that. Put reverse here. 4 meters per second in the reverse direction. This is minus VC2. Then get the sum of these two from triangle law. That presents the sum. This is velocity of the first car as observed by the second observer. This is the angle at which he is seeing him, as if he is moving. As if you take it as beta, he will be seeing like this. If you take with respect to vertical here, he will write here. This angle as beta. That means this angle as beta. Whereas that was like this. VC21. It was the angle alpha. What is the value of this one? Once again you can see it is 3 square plus 4 square only. That is VC2 in magnitude. This again 5 only. Even this was 5. We have worked out there. 5 meters per second. So this angle also is as this. You can see if you take tan beta, you will find here also tan beta is 3 by 4. The only question is, each one will find as if the other either is moving away from them in a different direction than actually they are moving. Actually they are moving at right angles to each other. So this is the illusion we are generated because of the relative velocity concept there. Observer should be at rest to know the actual velocity. If the observer is moving, his velocity also will be coming overshadowing there in the opposite direction in finding the actual velocity there. So that is what the concept tells us. Where do we come across that things? One example I gave you like this, when we are moving on the roads like that. Still we have got more important examples, so you can see them. Take the example of a riverboat problem. This is a famous thing that people say, often quote with reference to the relative velocity things, riverboat problems. In the riverboat problem, what happens is, suppose there is a river that is flowing like this. in this direction. That is downstream. That is velocity of the river, we say, suppose. This is with respect to the earth. And a boat starts here. It wants to reach at this point. It is going with the velocity here, suppose. That is the velocity of the boat. With respect to the river here, it starts like that. So what happens? We have given just now the notation that velocity of B with respect to R is equal to velocity of B with respect to the ground, that is earth, plus velocity of river with respect to that also. So this velocity of the river, this plus that will give you the velocity of the boat with respect to the earth. With respect to the river, it is moving. That means the boat, who is driving the boat, the sailor thinks as if he is heading up straight away. But what is happening? He is not going straight away. He is going in a different direction because this velocity is superimposed by that velocity. So this will be the actual velocity. One fellow who is on shore here, he will see this. Whereas the boat fellow will be seeing as if he is moving straight away. He cannot see that because he is not able to see the flow of the river with respect to himself. He is already in that. So he will see that. So this will be the actual velocity of the boat. This is actual velocity, we call it. So ultimately, because everybody moves in the direction of its velocity, his velocity only, so he will not reach here, he will reach here at this point. So if this is O, this is A, he will reach at B. He will not reach at A. Suppose he wants to reach at A directly. He must have an idea before starting itself that with this river is flowing with velocity. That velocity is VR. So I must not head straight away. I must head away like this. So he must head like this. He heads like this so that the river velocity, his velocity with respect to the river, plus the river velocity here, will give him the velocity with respect to the ground. Then this becomes the actual velocity. In that case, this becomes the actual velocity of boat with respect to the earth here. This is river velocity with respect to the earth. So this is short. So what we want to see is, it depends upon how you are heading up now. If you want to reach the opposite end, you have to head starting from a left side. Upstream must start here. If you start straight away, you will reach downstream there by this angle. There is a problem there. So you have to understand how to work such problems. We will take a numerical example and see here. A river is flowing with a velocity of 4 meters per second, and a person wants to cross that river to reach the opposite point here from here, and he starts with a velocity of 5 meters per second, suppose. That is the velocity of the boat. In which direction he must go? He must go in a direction upstream here, because to reach the opposite point he must start like this. So what will be the actual velocity with respect to the stream? Velocity of the boat with respect to the stream, and velocity of the boat with respect to the earth. He is now taking up this velocity with respect to the stream and comes like this, just head like this, so that this velocity is superimposed on this further, and this becomes the velocity of the boat with respect to the earth here, the velocity of the boat with respect to the river. You must take up at this angle alpha. How do you get this angle alpha? From the equations. Tan alpha is equal to VR in magnitude by VBE with respect to the or you can take with respect to the sine, we can take sine angle, sine alpha with respect to the river. This will be the actual velocity for him actually. He is with respect to the earth. That we don't know. He is starting with this. As if he is starting in the river, he starts like this. So he goes to the opposite end then. So in this case, our problem here, this is 4, this is 5. So alpha is equal to sine inverse of 4 by 5. You have to work out this and get the answer there. So this is the way in which you have to find out the angle there. Suppose what is the actual velocity now? You want to find out that also. This is given from the right angle triangle here. It is square root of 4 square plus 5 square. This is 5, that is 4. So it is 4 square plus 5 square. So this is equal to 16 plus 25 under root. How much time that will take from here to there? You will find time given is the distance travelled by the velocity. Here the velocity is, this velocity must take. It is travelling like this ultimately. From this end to that end. Width of the river suppose is d. We call it as 1 kilometer suppose or 0.5 kilometers suppose given there. D is width of the river. Equal to 0.5 kilometers. Then you see how it moves. This is 0.5 kilometers, therefore we put into meters. Then this is, you can simplify and put the answer there, whatever it is. So like this, we must be able to get the time. So if you want to cross in the shortest time, then you must head like this. Shortest distance across exactly. If you want to cross with the shortest distance that you want to take, that means from opposite end to opposite end you want to go like that exactly, then you must start up the stream with an angle alpha given by this equation. Here it will take more time because you are heading up the stream and you will push like this from there. Suppose you want to take least time, then you start directly straight away. Then you are going down the stream, river also is down the stream, both velocities will help you, and you will reach a point not in the same place, a different place. This will take shortest time, this will take the shortest path here. So for shortest path, you must head straight away. To reach the opposite end, you have to go like that. So where to start from? To start from upstream like this. Then you will reach the opposite point. Suppose you want to reach anywhere, all right, but you must go in the shortest time. Your velocity must be more. That means your velocity along with that should be given there. This goes like that in the direction. So here also the same velocity will come. This also 4 square plus 5 square under square root only. But the direction is here. So what is happening? It is taking more time to come here. Here direction is this. So it takes less time to go there. So shortest time and shortest distance. These are two conditions we have. Such problems come up even the flights. When you are moving in aeroplane, in the flight, you will see the pilot inside will not be able to see the air. He thinks as if he is going in one direction. Say, air is moving in the perpendicular direction there. Then he will be drifted according to the air. So relative velocity once again in the same way. Just like air, here it is a river. Similar problem there. The air is here is similar to river. The boat is flight there. The only difference is in the case of the boat and river, we are moving on the ground only. In the case of the air flight, you may be going in 3 dimensions there, and there will be a 3-dimensional flow of air also in a different direction there. Accordingly, the change of direction will be there, relative velocities will be there. So depending upon the problem, you can always set it up. Another example I give you. Suppose you are walking in the rain. You are walking in the rain, suppose. Then the rain, suppose is falling straight away like this. It is falling directly, pouring down vertically. And you are going in a car like this, moving forward direction. For you it appears as if it is coming in the direction like that, inclined there. Actually this will be coming straight away. Simple case, suppose a man is walking in rain with an umbrella. If he holds the umbrella straight like that and the rain is falling straight away like this, he will get drenched. He finds the rain as if it is coming inclined to him. So he has to hold the umbrella inclined there. It is like this. Suppose he is moving on the ground like this, in that direction. Velocity of the man, we call him Vm. With respect to the earth, that is stationary earth. Rain is falling here, velocity of the rain with respect to the earth, we call it again stationary earth. Rain is only falling on it straight away. The observer will find the velocity of the rain as measured by the observer you want now. So what will you see? Actual velocity of the rain plus the reverse velocity of the man. Man will see his velocity also in that direction. Opposite, reverse velocity. See here. This is plus, this is minus. So resultant of these two taken from the triangle gives you the velocity of the rain with respect to the man. It appears as if it is an angle here. So he has to hold the umbrella here in that direction there. Then only he will find like that. Actually, rain is coming straight away. So these problems can be tackled like that. Right? So you can use these concepts, and the angle also can be known in the same way, like you can take the tan alpha is given by opposite side by adjacent side in magnitudes if you take with respect to the earth, with respect to the earth. You can see in which direction he has to hold the umbrella means you can calculate like this. Values with what velocity is finding the rain come there, that is given by this equation from the vectors again here. This is V m square plus V r square. This is the usual relative velocity equation what we have. So concept relative velocity therefore comes because of the illusion generated because of the motion of the observer. If the observer is still only, he can see the actual motion. If he is also moving, he will see his velocity also in the reverse direction on the observed scene there. That's why it appears like that. Right? With these concepts, you can try the problems given in the book and then try to get to the concept more in detail. Thank you.